Today we're talking about auxiliary tasks and how they can be used, or rather learned automatically in a reinforcement learning setting. So normally, when you define auxiliary tasks, they are something that your user, or let's say the RL developer, develops using or manually puts in place using expert knowledge. And this is a problem because if you have an algorithm, it's sort of dependent on how well you can construct those auxiliary tasks. And so if you have a human interference there, or basically the human needs to specify them, the solution is only going to be so good as the human is able to provide when it comes to these tasks to help the agent out. So what you want to do is you want to get away from this optimally, right? So you would want some algorithm that can learn by itself and increase, let's say, the speed at which it's learning and the effectiveness of its own learning algorithm as it goes. And this is called meta learning. So you're sort of one step above the actual learner that's learning about the environment, and you're learning about how you can learn the environment. And specifically in this paper, so this is a Google DeepMind paper, and they're talking about how to implement, this sort of meta learning and how you can actually define those tasks in an automated way. And the specific approach that they're using is something called meta gradients. So this is a subset of meta learning. So we consider an agent or a learner. So in the sentence that we have here, that's the last word here. This learner is the one we're concerning ourselves with. And when we update that, normally we do so with some sort of gradient ascent. But now we parameterize that update. So we don't simply update by a simple gradient with respect to that learner, but we use the meta parameters, so these parameters, to tailor exactly how we update the learner itself. So the meta learner then, to look at the sentence in its full form, the meta learner is trained via gradients through the effect of the meta parameters on the learner. So you consider the effects of the meta parameters on the learner, and then you use gradients to train the meta learner as a second step. And this is the overall approach that you take to tackle these problems. And if we compare this to what's normally done in a reinforcement learning setting when we try to learn things, we basically pose a question to ourselves. So we ask ourselves what the discounted sum of future rewards is under some policy, and that's what we're trying to solve when we approach this in the standard way that you normally would. The answer to that question is the approximate value function, and that's what you try to get in using your various algorithms that we can employ. In order to specify these auxiliary tasks in an automated way, what we're going to make use of, or what they make use of in this paper, is something called generalized value functions, or general value functions. These GVFs are a generalization of the standard value function concept. They are basically, in this framework, you replace the standard value function with an arbitrary cumulant function, is what it's called. And this is more, let's say, expressive, so you can express more general predictive knowledge using this sort of framework. And a good thing about the framework is that a lot of the methods, like TD methods for training your algorithms, also extend to the GVF framework. So it's sort of an extension of the concept that doesn't really hinder us much in terms of what algorithms we can apply. So that's a very good thing. And when we then provide these generalized value functions, they tell us something about the environment. So they are what we would call as auxiliary tasks. And as you may know from previous talks that we had, auxiliary tasks are a way of helping to shape the representation of a problem to better align with the task that you're trying to solve. So normally, if you have an environment where, let's say, the rewards are very sparse, you could have problems with the agent not actually attaining any rewards, and therefore the state representation not really getting better. And so that's a problem you want to address, right? And you can do that with the help of these auxiliary tasks. So if you define those, basically what you can do then is they will help you in shaping your state representation, and that will give you a more efficient way of learning the task itself. And these general value functions will then be used as auxiliary tasks. So they provide us with, intermediate tasks that we can solve, and those tasks hopefully will help us then converge to a good representation that will help us learn the optimal action value function. So that's the idea behind this. And we need to now find a way to automate this. And that's what they're addressing. So what we will propose now is basically have a look at the architecture that they're using in this paper. They're using two networks within the paper. And the first one, which we can see on the top here, is very similar to what you would have in a standard reinforcement learning application, where we're not considering these auxiliary tasks to help us in our in our objective. So what we have here in the main task and answer network is you get a set of observations. So you get a set of historical observations, and the output of this network would then be a policy, pi t, and also answers to these general value functions. And in addition to this standard network, we have something called a question network they're using. And the purpose of this network is to generate these outputs that we see here. These are cumulants and discounts of the general value functions. So the GVFs are specified by 3 parameters, namely the cumulant, so that's the equivalent of the reward function, the discount associated with it, and then also the policy. And from this network, we can see that we only have 2 outputs, right? We don't have a policy here. And the reason for that is because they're considering a on-policy setting here. So it doesn't really make sense for you to print out or like to give the policy as an output if you're already acting according to, well, to the policy, because then you know it per default. So that would only make the network bigger for no reason whatsoever. So that's why they only have these 2 outputs here. And these outputs are also vectors. So it's not only that you're constructing one cumulant or one auxiliary task for your agent, but you're constructing a number of them. So you might know if you watched previous auxiliary task videos that you can make use of several of them to actually converge at a better representation. So these are vector valued outputs. So now that we've gone over the network and the network architecture, we want to actually have a look at the updating steps that we would do in practice. Basically, we want to take a series of steps with our learning algorithm that is parameterized by the meta parameters. And after we've taken those steps, we want to evaluate how well did it perform during that period of time. And once we have that feedback, we can then reassess our meta parameters and try to adjust them. The thing you need to keep in mind is that when we update the meta parameters, the effect that we're going to see in terms of how well the results are is going to be, let's say, a second order effect. Because if we update the parameters, that's what we would have a direct effect on the output, or basically on our performance. But the meta parameters only indicate how we update the parameters themselves. So it will be sort of a delayed effect. And so it could be useful to do a number of updates in order to get better feedback as you transition or as you make use of your meta parameter updates. So to make this concrete, we perform a set of updates based on the parameterized gradient. So we have our gradient of network parameters. This is both for the action network and for the main network that we discussed in the previous slide. And we update them, and the update step has 2 loss functions included in it. So the first one is a standard reinforcement learning loss function. So that is sort of tailored to the main task. And then we also have a loss function relating to the auxiliary tasks here, where we try to approximate the answers to the general value functions. We do this for a number of steps, and then we measure the performance in terms of the meta loss. And the meta loss, what we use for that is basically the sum of loss functions for all of these steps, but only for the reinforcement learning, so the main task loss function. The reason for this is when we update the network parameters themselves, we want to make use of the auxiliary tasks to get a better state representation. That's what we talked about in the early parts of this video. But when we actually evaluate the meta parameters and tailor the learning algorithm for those, what we're interested in is actually performance. And so we update or we use the meta loss function to, we only let the meta loss function depend on the losses for the main reinforcement learning task. And so the change in parameters for this meta learner are indicated down here. So you will basically have an update step which depends on the loss of your reinforcement learning task. We want to have a look at some results now, and in order to have a meaningful comparison to other methodologies, we want to have a look at some auxiliary tasks that we would define basically for comparison purposes only. So the first thing we want to have a look at is something called a reward prediction. This is a no question architecture. So basically what we're saying is we don't have this question network. We only make use of the main task and answer network. And what we try to do is we try to estimate the reward of the next time step. So we can see the loss function right here, which is basically just our approximated value minus the reward at time t+1. And then it's an MSE. So, we square the error. Next thing is pixel control. And this, similar to the reward prediction, is a no question network, or it doesn't have a question network. And the auxiliary task here is to learn to optimally control changes in pixel intensities. So one thing that you could imagine is that the agent gets stuck basically just walking toward a wall and not really exploring anything. That's something you would want to, get around. So you want pixels to change. Just having pixels changing at a high rate is not enough to get to a good strategy, but it could be a helpful task, and therefore we define it as an auxiliary task. And what this auxiliary task objective is then is to maximize the average pixel intensity change for each cell in an n times n non-overlapping grid. So we don't take one chunk and basically just consider that, but we have multiple grids and we want to maximize the pixel change in each one of those. The last one is something called random questions, and this is almost the same as the metagradient-based agent. So the architecture is very similar, and we have a question network then that parameterizes, or where the parameters are randomly initialized and kept fixed through training. So we don't update them at the training steps. We just initialize them and then we let them be, just to see sort of what the architecture produces. And the answer network then is still trained to predict values for cumulants from question network. So you train the answer network, but you let the question network be. So these are the initializations. And the last one, I mean, you can tell from the name, this is random questions. We have, because we don't update the question network, our question is going to be random and they're going to stay the same. But based on those, we try to then update the answer network. So we see the effect of having, let's say, just the raw architecture of a question network. And the first environments that we're going to evaluate this on are something called puddle world and then collect objects. So if we start with the collect objects that we can see up here, it's basically a environment, a grid world environment, where we have 4 rooms like this. There are 2 rewards placed in these rooms, and they're placed the same position every time. What the agent should do is it should find these and basically select them, but it needs to do it in the correct order. So the agent is going to be randomly initialized somewhere in this domain, and it needs to find the first one and then the second one. And we can see here that it gets a reward of 1 for picking up the first object and a reward of 2 for picking up the second object after the first one. So you need to do it in the right order. And as I said, the starting position is random, but at least the environment is deterministic. So you get to move around here and then you need to select them in the appropriate order. For the second world, this is called puddle world, and it looks like this, or this is a picture of it. So you're initialized somewhere in the grid, and then you need to make it to basically a goal, which is up here in this case. You need to avoid the puddles. So you need to basically go around them, but it's more complex in the sense that the environment is also stochastic. So you can see on the trajectory selected by the agent here, it actually moves in the wrong direction, it seems, over here. But it might make sense if the environment is stochastic and you want to avoid basically, getting pushed into this puddle here. So those are the 2 tasks. And if we look at the performance now, we can see the discovered GVFs in red. So this is the one that we're, optimistic about and what that actually uses the framework we developed. We have A to C, which is just an actor-critic model. And then we have random GVFs and reward prediction in this graph. And the first thing we can note is that A to C is basically up here on top for both of them. So we see a very fast convergence in the actor-critic network, and all of the other ones using auxiliary tasks here are more slow to converge, or are slower in convergence. What we can also see is that the discovered GVF reaches the level of the A to C for both of these. And in fact, the level up here is the optimal level that you can attain. So both of these cannot get any better. So we perform optimally in the 2 state spaces. Because these are quite simple, the agent is actually able to learn the optimal policy here. However, we can see that for random GVFs and reward prediction, the performance is significantly worse. So we definitely see a better performance with the GVF in these simple environments than we do for the other algorithms. We're going to transition to some more complex domains now that we've seen the performance of these more simple tasks. And for that, as often is the case with reinforcement learning agents, we consider the Atari suite of games. So here we have 6 of the Atari games printed basically in performance, and we have the same notation as we had in the previous slide. So discover GVFs, which is our main algorithm of choice, is indicated in red here. What we can see is that the handcrafted auxiliary tasks for most of these figures, or for all of the figures, are significantly below the discovered GVFs, and they don't really result in any good state representations. So we can see for all of them that we tend to have a mix of the green, purple, and blue lines that indicate these various auxiliary task choices, significantly below the discovered GVFs. And in addition to this, maybe the most interesting result on this graph is that for Gravitar and Frostbite, so the 2 games to the top right here, in those 2, we actually perform, or we actually notice a significant outperformance of the discovered GVFs in comparison to just the Impala algorithm. So here we actually outperform the standard algorithm that you might come to use in a situation like this. So those results are quite interesting. In addition to just these pure results, we also have results when it comes to the hyperparameters of this architecture. So we discussed in the beginning that we have vector value quantities going out from our network. We can have a look at it again. So in the question network here, we said that the cumulants and discounts are vector valued because we could have a number of auxiliary tasks and well, a number of questions that we ask ourselves. And so this is what we're investigating with the top left figure here. So this is the number of questions, and then we have performance on the axis here. And what we can note is that we have, when we have few questions, so in the left part of this figure, we see a decrease in performance. The reason for this is that the state representation resulting from these few tasks is not sufficiently good to basically get us to, to a good performing region. In contrast to that, we can see in the right-hand side here that we also tend to drop in performance. It's not as clear, but it seems like we're starting to drop at the right-hand side of this figure. And what the authors postulated this is for is that learning becomes slower as you increase the number of auxiliary tasks, just because you have more network parameters to learn. And because we're dealing with finite resources, that will basically have a consequence on training. So you won't be able to train as well if you have a very large network, and that is what we observe in the right-hand side of this graph. The other hyperparameter that we want to investigate is something called the unroll length. That has to do with how we evaluate the metagradient. So when you evaluate the metagradient, you don't necessarily do that in one step, but you do it in several steps. And we didn't go into so much of the technical details and exactly how that is evaluated, but nevertheless, the number of steps that you take into account is something called the unroll length, and that is a hyperparameter that you can also tune. And similar to the number of questions, we see that if we have a very short unroll length, we tend to suffer in performance. And that's because our estimates of the gradient become less accurate. However, on the right-hand side here, it seems like performance might taper off as well. It's not evident that it's always going to increase. And the authors postulate that the performance will, that you will potentially get an increased variance when you evaluate the metagradient if you have a very long unroll length, because you take like many steps, and so you get a larger variance because more can happen in that interval, let's say. The final thing that we want to look at is something called joint learning. And what we're doing here is we're sorting our games according to the pixel control gains over the Impala algorithm. And for the top figure here, we're only including the top 10 games. So for the Atari suite, we have more games. We have 57 games in total, but we're only displaying the top 10 here. And those are not the top 10 games for discovered GVFs, but they're the top 10 games for pixel control. And what we can see here in this figure is the performance of the discovered GVFs over Impala. So for everything that's above 0 here, we basically have better performance for GVFs compared to Impala. And for Berserk and Assault here on the left-hand side, we have worse performance of GVFs compared to Impala. So we can see that for the majority of games here, even though they're not sorting according to GVFs in particular, GVF tends to actually produce quite well on these tasks. And for the figure at the bottom here, that's a bit more comprehensive. So it includes the full suite of Atari games. We can see the number of Atari games displayed down here, and it goes all the way to 57. What we can see on the y-axis is the median normalized scores in %, and basically all the different algorithms according to the color coding that we used previously. So we can see Impala here. That is sort of the baseline, I guess, or what we're trying to, increase performance, the algorithm that we're trying to improve. And discovered GVFs is the red graph here. And similar to the top graph, it's sorted in terms of performance for pixel control compared to Impala. And for pretty much all of these games, I mean, the majority of them, we actually have a performance increase for discovered GVFs as opposed to Impala. There are a few games here at the end where that is not the case, but in general for these, it seems to perform better with discovered GVFs. And that is, I would say, the main conclusion that you can draw from this paper is that for the settings where auxiliary tasks are actually useful for learning a task, implementing the algorithm of metagradients and discovered GVFs tends to be a good approach. Like we tend to see better performance using that algorithm than the other ones. However, for all kinds of games, it's not evident that auxiliary tasks are preferable to begin with. And in those settings, this algorithm would not necessarily, make it preferable. So it's not as easy as you can apply this to all settings, and you will basically get an outperformance compared to a more simple agent. But in cases where auxiliary tasks really do make a difference, then it seems like this framework would be a very good addition to the standard hand-tailored auxiliary tasks that have been built up to this point. So that's it for now. Thanks for watching, and see you in the next video.